So we'll look at an example of the chain rule used to understand the ideal gas law. So the ideal gas law here is the old PIV NERT, right? So here P is pressure, V is volume, T is temperature, and N and R are some physical constants that gassy people care about, apparently. I don't actually remember what they are off the top of my head. Something with moles or some physical constant, whatever. Doesn't matter. The first thing that we're going to do, since we're in a math class, is we're going to assume that NR is equal to 1, so that we can just get rid of that term right there and make life simple, because this is a math class. So let's see. So how is pressure changing when temperature is 300 degrees Kelvin and increasing at 0.1 degrees Kelvin per second, and volume is 100 liters and increasing at 0.2 liters per second? So what's going on here? So with this relationship, if the temperature is increasing, then that would tell you that the stuff on the other side is increasing. But we also have volume increasing. So then it's kind of a tug of war. Like, is volume increasing fast enough that pressure has to be going down? Or is volume increasing slowly enough that actually, in order to keep pace with T, the pressure has to increase as well? Okay, so let's figure this out. Well, the first thing to notice is that we are kind of controlling what the temperature and the volume are. So we're thinking of these guys as being independent. And in other words, we're thinking that pressure is a function of the other two variables. So we're thinking pressure depends on temperature and volume. And then in that case, what it would be equal to is just, we would take this expression and solve it for P, which fortunately we can do, and we get T over V. Okay, so then for the chain rule, if we want to figure out how fast pressure is changing with respect to time, then this is going to be the rate of change of P with respect to pressure with respect to temperature times the speed at which temperature is changing, plus the rate at which pressure changes with respect to volume times the rate at which volume is changing. Okay, so this much so far. This is just formal. I haven't actually done anything here. This is just the notation for the formula of the chain rule. Now, in the next line here, I'm going to actually do the computation. So we know we've got our formula here for what P is in terms of T and V. So I can differentiate this guy with respect to T. And so dP dt is going to be 1 over V. And then I don't know what this thing is yet. And if I differentiate with respect to V, okay, so then what do I get? I get actually minus T over V squared. So the derivative of T over V is minus T over V squared. And then I have dV dt. Okay, so there's now my expression for what this is in terms of the chain rule. And I don't know the general formula for d temperature, d time, or d volume, d time, but I am given specific values for them over here. So this increasing at this rate here, that's going to be my rate of change of the temperature, and increasing at this rate, that's going to be my speed at which the volume is changing. So I can, now let's see, I can substitute these in. So for my volume, what was, so that's 100 liters. So I'm going to take, shoot, I need another color. Here, let's go orange. So volume is 100 liters. So I'm going to go from that and substitute in here and say, okay, so I've got 1 over 100. And then I've got my d-temperature, d-time, and that was 0.1. And then I have minus, and then temperature is 300, and I'm out of colors again. Here, let's go red. So based on the fact that temperature is 300, I've got 300 over, and then volume squared, which is, get my orange back, 100 squared there. And then I have times dV dt, which was 0.2. Okay. And then, so now we do the computation of rainbow bright here, and we've got 0.001 minus 0.006, and then we have some answer, minus 0.005. Okay, so I guess volume is going up fast enough to match temperature that the pressure is going to drop. So the negative sign meaning decreasing. And we have that in some units that matter to somebody. Okay, let me just point out, as I mentioned in a previous one, and that is that we substitute the given values last, and that's a key point, right? That happened right here at the very end after we did all of our differentiation. I'm just harping on that because that's the number one most common error that people make when they're doing problems like this.